In the face of increasing global water challenges, the sustainable management of groundwater resources has never been more critical. Good day, I am DJ Tabion, and I'm excited to share with you a study that addresses a critical issue in arid and semi-arid region. The study is titled Estimation of Aquifer Hydraulic Parameters Using Electrical Resistivity Method, a case study for Damaturu, Northeast Nigeria. Let's delve into understanding the background of the study. Proper understanding of aquifer parameters is essential for effective management of groundwater resources. The increasing demand for groundwater in recent times due to population growth, agricultural and industrial expansions requires explicit quantitative description of aquifer parameters in any given location in order to facilitate easy access and equitable provision of groundwater resources. On the other hand, several researchers have used electrical resistivity method to delineate and evaluate aquifer properties in various locations around the world. Electrical resistivity method has proven to be a veritable tool for groundwater exploration over the years, and its efficiency depends on soil saturation, porosity, fluid dynamics, permeability, groundwater chemical composition, and rock lithology. By employing the electrical resistivity method, a non-invasive technique, this research aims to delineate and estimate key aquifer parameters. The findings of this study provided valuable insights for groundwater exploration, abstraction, development, and pollution control, ultimately contributing to the well-being of the communities that depends on this vital resource. Damaturu is located on latitude 11.744 degree north and longitude 11.961 degree east. It is within the GEOE state, northeast Nigeria. The study area experiences an annual rainfall of 600 mm and evapotranspiration of about 2000 mm. The study area is located within the Chad Basin, which extends across Chad, Nigeria, Cameroon, Central African Republic, and Niger. Approximately 10% of the basin is situated in northeastern Nigeria, covering parts of Borno, Yobe, and Jigawa states. The Chad Basin resulted from the plate divergence along the West Africa continental margin, a process involving regional thermal doming, volcanism, rifting, and sedimentation. Groundwater resources in Damaturu originate from the Chad Basin's aquifers, which include upper, middle, and lower zones, primarily composed of sandy formations separated by clay and sandy clay. The Chad Basin aquifer has experienced a considerable decline in the water table. The aquifer consists of fine to coarse-grained sands, with the upper aquifer with some areas of Damaturu occurring under phreatic conditions and being recharged directly by infiltration of surface rain runoff. The study was carried out using the following materials: Global Positioning System or GPS, ABEM SAS 100 digital thermometer, personal computer, electrodes, reels of cables and jumpers, hammers, measuring tape, 12 volts car battery, pegs, ABEM SAS external battery adapter, Surfer 11 software, and Origin Pro 2017 software. Electrical resistivity method involving Schlumberger array was adopted for this study. The field data acquisition was carried out by laying electrical cables along predefined profiles, and the cables were linked to the ground using sets of electrodes and cable jumpers. An electrode test was performed to ensure that current was flowing through all the electrodes, and the inner electrodes are the potential electrodes and the outer electrodes are the current electrodes. 20 vertical electrical sounding or VES were carried out in the study area with the aim of delineating the various subsurface layers, for thicknesses and depth to groundwater and overburden thickness. ABEM SAS 100 thermometer was used to measure the resistance, voltage, and current of the soil. And for the data analysis, the resistivity data were interpreted to delineate subsurface layers and estimate aquifer parameters. The apparent resistivity values were obtained by multiplying the resistance by the geometric factor, and the subsurface layers' resistivities were modeled using Palaki 1988 through resistivity value chart. The study area comprises 5 geologic layers, which is topsoil, clay, sand, sandy clay, and sand. The first layer has 0.7 meters to 2.6 meters thick, is a mixture of humus, clay, and sand. The second layer is clay, which is 4.5 meters to 12.2 meters thick, overlies the third layer, which is the first aquifer. This clay layer's proximity to the surface contributes to flooding during the rainy season. The third layer has resistivity of 126.4 ohm meters to 516.7 ohm meters, with a thickness of 38.77 meters to 71 meters, is sand deformation and the first aquifer. The fourth layer is sandy clay. It has thickness of 50.3 meters to 96.4 meters. Layer thicknesses indicate Damaturu's location on the Chad Basin fringe, with increasing thickness towards Maiduguri. The second aquifer's depth precluded thickness determination. The third and fifth layers are sand deformations, constituting the semi-confined first and confined second aquifers. The aquifer parameters, including transmissivity, hydraulic conductivity, porosity, tortuosity, and formation factor, were estimated using established models. Aquifer porosity in the study area ranged from 30.13% to 31.44%, with an average value of 30.6%, and it's almost uniform due to its stratification. Porosity is slightly higher towards the southwestern part of the study area. Aquifer transmissivity ranged from 62.7 to 194.6 meters squared per day, with an average value of 111 meters squared per day. Based on the average transmissivity value, the aquifer potential of the study area is moderate. Transmissivity is higher towards the southwestern part of the study area, and higher porosity is associated with high transmissivity. This table shows that the aquifer in Damaturu area has varying characteristics, demonstrating moderate hydraulic conductivity and transmissivity, indicating a moderate capacity to transmit groundwater. The porosity values suggest a reasonable amount of water storage capacity. Next, we will discuss the contour map of the study area that represents different aquifer parameters that is gathered through ERM or electrical resistivity method. Figure 4 presents a porosity contour map of the study area. The map illustrates the spatial distribution of aquifer porosity, a measure of the void space within the aquifer material across the region. As the image indicates, the aquifer porosity is generally higher towards the southern part of the study area. The contour lines show how porosity values change geographically, with different colors representing varying ranges of porosity. These suggest that groundwater storage capacity, which is directly related to porosity, is more significant in the southern portion of the study area. Figure 5 illustrates the spatial distribution of aquifer transmissivity within the study area. Transmissivity is a measure of aquifer's capacity to transmit water, is shown using contour lines with different colors representing varying transmissivity values. The map indicates that transmissivity is generally higher towards the southwestern part of the study area, suggesting greater potential for groundwater flow in the region. In contrast, transmissivity is lower towards the eastern part, indicating reduced groundwater flow potential. The remaining areas exhibit moderate transmissivity. This spatial variation in transmissivity is crucial for understanding groundwater dynamics and for effective water resource management in the Damaturu area. Figure 6 shows the spatial distribution of hydraulic conductivity within the study area. Hydraulic conductivity is a measure of how easily water flows through the aquifer. It is represented using contour lines. The different colors on the map indicates varying values of hydraulic conductivity. As the figure illustrates, Hydraulic conductivity is generally higher towards the southwestern part of the study area, suggesting that groundwater can flow more readily in that region. Figure 7 displays the spatial distribution of aquifer resistivity within the study area. Aquifer resistivity is a measure of how much the aquifer material resists the flow of electrical current and is represented using contour lines. The different colors on the map indicate varying values of aquifer resistivity measured in ohm meters. As the figure illustrates, the resistivity of the aquifer is generally higher towards the southwestern part of the study area and moderate in the eastern part. Figure 8 illustrates the spatial distribution of aquifer thickness within the study area. Aquifer thickness, representing the vertical extent of the aquifer, is shown using contour lines. The different colors on the map indicate varying values of aquifer thickness. As the figure illustrates, the aquifer thickness increases towards the eastern part of the study area. Figure 9 illustrates the spatial distribution of aquifer tortuosity within the study area. Tortuosity is a measure of the complexity of the path that groundwater must flow through the aquifer material and is represented using contour lines. The different colors on the map indicate varying values of tortuosity. As the figure illustrates, the tortuosity is generally higher in the southern part of the area. Figure 10 illustrates the spatial distribution of the aquifer formation factor within the study area. The formation factor is a dimensionless quantity that relates the electrical resistivity of a rock to the resistivity of the fluid it contains, and is represented using contour lines. The different colors on the map indicate varying values of the formation factor. As the figure illustrates, the formation factor is almost uniform across the study area, considering its range, which is 0.1105 to 0.1129. Furthermore, the results of the assessed hydraulic parameters of the aquifer have revealed that the aquifer in the study area has good groundwater potential, and it also has appreciable porosity for effective groundwater flow and storage. These evaluated aquifer parameters will help to provide the basis of groundwater exploration, abstraction, development, and protection. To conclude, this study devoted to estimating the aquifer parameters in Damaturu, northeastern Nigeria using electrical resistivity method. In this study, vertical electrical sounding or VES, which involves Lumberjay configuration, were used to characterize the aquifer parameters. The results showed that the study area has good groundwater potential and it is susceptible to pollution due to porous nature of the study area. The proximity of the first aquifer to the surface requires an enhanced protection to secure it from contamination. The results obtained in this study will serve as good basis for effective groundwater development and protection. Significantly, the result will be used to control environmental pollution leading to groundwater contamination in the area. Thank you for listening. Again, I am DJ Tabion. This is the study titled Estimation of Aquifer Hydraulic Parameters Using Electrical Resistivity Method, a case study for Damaturu, Northeast Nigeria.